Hey everyone, welcome back. Today we're going to be diving deep into QUIC.
QUIC. It's definitely a hot topic these days. Everyone wants faster internet, right?
For sure.
Yeah.
I was just trying to download this huge video file the other day, and
It took forever.
it felt like it, yeah. So we're really excited to take a closer look at this new protocol and see what all the fuss is about. Specifically, we're going to be digging into this research paper with a very interesting title.
Oh, yeah.
QUIC is not quick enough over fast internet.
Very provocative.
It is. QUIC is supposed to be all about speed, right?
Well, yeah, that's the whole point. Quick UDP internet connections. It's the foundation for HTTP3, the next generation of the web.
So why are some researchers saying it's not living up to the hype? Especially when it comes to high-speed internet connections.
Right.
So, to be clear, when we say QUIC, we're talking about the whole shebang.
Yeah.
UDP plus QUIC plus HTTP3. We're comparing that to the traditional TCP, TLS, and HTTP2 stack.
Yep, apples to apples comparison. So the researchers set up a series of experiments to see how QIC performs compared to HTTP2.
Which is what we're all using right now, basically.
Pretty much, yeah. So they started with a simple file download scenario, used tools like CURL and QUIC client.
Kind of like command line tools for downloading files.
Right, exactly.
So did QUIC blow HTTP2 out of the water?
Well, not quite. Actually, what they found was kind of surprising. On slower internet connections, QUIC did okay. Sometimes it even beat HTTP2 by a little bit, but as they started to increase the bandwidth, things got interesting.
So on faster internet connections, QUIC actually started to slow down.
Yeah, it's counterintuitive, right?
Yeah.
But that's what the data shows. At 1 gigabit per second, which is pretty standard these days.
For some people.
For some people, yeah. QUIC was up to 15.7% slower than HTTP2 when using those lightweight clients.
So a noticeable difference already.
Mm-hmm.
But I imagine it gets worse when you factor in real-world web browsers.
You're telling me. When they tested with Chrome, Firefox, Edge, the performance gap was even bigger, up to 45.2% slower on Chrome at 1 gigabit per second.
Wow, that's significant. I mean, we're not just talking about downloading files faster here. This affects everything we do online.
You got it. Streaming video, browsing the web, video calls, online gaming. Anything that involves transferring lots of data quickly.
So the researchers were obviously curious. Why is QUIC, which is designed for speed, struggling on fast connections?
Right. It's a real head-scratcher.
Yeah.
So they had to rule out a bunch of possibilities, right? Like, was it the server software? Was it something specific to UDP versus TCP? Was it the encryption?
So they went through and eliminated all those usual suspects?
Yeah, and it wasn't any of those things, so they had to dig deeper. They started looking at what are called packet traces. It's like a digital fingerprint of how data is moving across the network.
Okay, so what did these packet traces reveal?
Well, they found that QUIC was receiving way more packets than HTTP2, even though they were sending similar amounts of data.
Wait, hold on. More packets for the same amount of data? Shouldn't that mean it's slower?
You would think so, right? But TCP has this neat trick up its sleeve called generic receive offload, GRO. It basically bundles multiple packets together into larger chunks, making them much more efficient to process. It's like taking a bunch of small packages and putting them into one big box.
Ah, so TCP is streamlining things behind the scenes, but QUIC isn't.
Not in the same way. And this difference in packet handling leads to much higher CPU usage on the receiver.
Because it has to process all those individual packets. It's like trying to drink from a fire hose instead of a regular garden hose.
Exactly. You can only process so much information at once.
So that's one piece of the puzzle, QUIC's lack of efficient packet bundling. But there's more to it, right?
Oh, yeah. They also found that the round-trip time, or RTT, was much higher for QUIC compared to HTTP2.
RTT is a measure of how long it takes data to travel back and forth between the server and the client.
Right. And the fact that QUIC's RTT was so much higher was a clear sign that something was causing a bottleneck somewhere, but it wasn't the network itself.
Intriguing. So where was this bottleneck hiding? We'll have to find out after the break.
Stay tuned. So the researchers, they had to go deeper, right? Like beyond the network level. They started looking at the operating system and even the browser code.
So it's like they were doing a digital autopsy?
Yeah, kind of, trying to figure out exactly what was causing this performance bottleneck.
Fascinating. So what did they find?
Well, first they discovered that the lack of UDP GRO on the receiver side was a major issue.
Right, we talked about that earlier, that packet bundling trick that TCP uses.
Exactly. Without UDP GRO, the kernel, which is like the brain of the operating system, It's bombarded with all these individual packets.
It's like trying to juggle a dozen balls at once.
Yeah. And remember, we're not just talking about servers here. We're talking about laptops, phones, tablets, all these devices that might not have the processing power to handle that kind of load.
So QUIC is actually creating more work for our devices.
In a way, yeah. Especially those without UDP+GRO. And to make matters worse, they found that Chromium, the open source basis for Chrome, was spending way too much time generating acknowledgments for each packet.
Acknowledgements.
Yeah, basically it's like a confirmation that the packet has been received. TCP handles this really efficiently at the kernel level, but Chromium was doing it in user space, which is much slower.
So it's like Chromium is sending a thank you note for every single piece of data it receives. Very polite, but not very efficient.
Yeah, good analogy. And all these little inefficiencies add up, right? They create a bottleneck that slows down the entire data transfer process.
Okay, so we've got QUIC's design itself, the lack of optimization on the receiver side, and the limitations of some of our devices. It's like a perfect storm of factors contributing to this performance gap. But surely there are ways to fix this right.
Of course. Identifying the problem is the first step. The researchers, they actually proposed a number of potential solutions.
Okay, let's hear them. I'm ready to roll up my sleeves and get this fixed.
All right. Well, the most obvious solution is to implement UDP+GRO on the receiver side.
Seems like a no-brainer. Just give everyone that packet bundling magic.
You'd think so. But the challenge is the internet is huge. There are so many different devices, operating systems, hardware configurations. Getting everyone on board with UDP+GRO is a massive undertaking.
Yeah, it's like herding cats. But even if we could get everyone to implement UDP+GRO, wouldn't QUIC itself need some adjustments to work with it effectively?
That's a great point. QUIC, with its multiplex streams and different packet sizes, it doesn't quite fit into the existing GRO mold.
So we need to make GR more QUIC friendly.
Exactly. It requires some clever engineering to handle those different packet sizes and to implement better pacing mechanisms.
Pacing.
Yeah, it's like when you're sending a large file, instead of just blasting it out all at once, you send it in controlled bursts. That gives the receiver time to process and acknowledge the data without getting overwhelmed.
So it's about finding the right rhythm, balancing speed with efficiency.
Exactly. It's like a dance between the sender and the receiver.
Okay, so we've addressed the need for UDP+GRO on the receiver side and making it more compatible with QUIC. What other optimizations did the researchers suggest?
Well, remember those acknowledgments that Chromium was struggling with?
Yeah, the thank you note marathon.
Right. Instead of acknowledging every single packet, we can use something called delayed ACKs. The receiver can acknowledge multiple packets at once, which significantly reduces the overhead.
So it's like sending one big thank you note for the whole batch of gifts?
Exactly. And they also suggested using a system call called refevmsg. It allows you to read multiple packets at once.
So instead of picking up one letter at a time from your mailbox, you can grab a whole stack.
Yes, it's much more efficient.
Okay, so we've tackled the kernel, we've tweaked GRO, we've optimized QUIC's acknowledgement process. Anything else?
Well, there's one more intriguing possibility. Multi-threaded download.
Multi-threaded, what's that all about?
So right now, Chromium uses a single thread to receive data.
A single thread. That's like having one cashier trying to handle all the customers at a busy supermarket.
Yeah, it creates a bottleneck. But if we spread the workload across multiple threads, each running on a separate CPU core, we could potentially improve performance significantly. It's like opening up multiple checkout lanes.
I see. But wouldn't that lead to problems with fairness? Like some threads hogging all the resources?
It's a valid concern. But there are ways to manage that, like using coupled congestion control to make sure the threads share the bandwidth fairly.
So we've got this whole arsenal of potential solutions to address QUIC's performance issues. But let's step back for a second. What does this research tell us about the state of QUIC and the future of the internet?
Well, I think it's a reminder that even the most promising technologies have their growing pains.
Yeah, it's like we built this amazing race car, but we forgot to put in a powerful enough engine.
Exactly. And it highlights the need to think holistically about optimization. It's not just about the network, it's about the software and the hardware as well.
So it's a challenge for the entire internet ecosystem.
Absolutely. Developers, hardware manufacturers, everyone needs to work together to make sure QIC reaches its full potential.
It's a reminder that innovation is an ongoing process.
It is, and that there's always room for improvement.
So what does this all mean for our listeners?
Well, next time you're streaming a 4K movie or downloading a huge game, remember that there's a lot of complexity happening behind the scenes.
And while QUIC might not be as quick as we hoped on those super-fast connections just yet, it's still laying the groundwork for a faster, more efficient, and more secure internet.
It's a work in progress, but the future of online connectivity is looking bright.
So to wrap things up, is QUIC living up to its promise? Not quite yet, at least on those fast internet connections. But this research helps us understand why. And that's the first step to fixing it. It's a reminder that even the most promising technologies, they have their growing pains.
It's true. What's fascinating to me is the potential for improvement. Imagine QUIC reaching its full potential. It could be the cornerstone of an even faster, more efficient internet. Or maybe there are fundamental limitations that we need to rethink. This research, it opens up exciting avenues for further exploration.
And that's the beauty of the deep dive. We give you the knowledge, and you get to ponder the possibilities. Thanks for joining us on this exploration of QUIC, and until next time, happy surfing. It really makes you think, all this stuff happening behind the scenes.
It does. We take it for granted, but there's so much complexity involved in making the internet work.
Right. We just expect things to be fast, but there are all these factors at play.
Yeah, and this research really highlights how important optimization is. Not just the network, but the software and hardware too.
So even though QUIC might not be living up to its full potential yet, especially on those super fast connections, it sounds like researchers are on the right track.
They are. They've already identified some promising solutions, and they're actively working on improving things.
It's exciting to think about what the future holds. Once these optimizations are in place, QUIC could really change the game.
Imagine downloading huge files in seconds, streaming 4K video without a hitch, online gaming with zero lag.
It's a future worth striving for. This research definitely brings us one step closer. But it also makes you wonder, right, is there a limit to how fast we can make the internet?
That's a great question. As we push the boundaries of speed and efficiency, we might run into new challenges that we haven't even thought of yet.
It's like we're constantly exploring new frontiers in the digital world.
Exactly. And that's what makes this field so fascinating. There's always something new to discover, new problems to solve.
So to our listeners out there, the next time you click a link or download a file, take a moment to appreciate all the amazing technology that's making it happen.
And remember that even though QUIC might not be perfectly quick just yet, it represents a huge step forward. It's paving the way for a faster, more efficient, more secure internet.
And that wraps up our deep dive into the world of QUIC. Thanks for joining us on this journey of discovery. Until next time, stay curious, keep exploring, and may your internet speeds always be blazing fast.